When you see an AI like ChatGPT write something, it's actually thinking one word at a time. But what if it could just grasp the entire idea all at once? What if it could sculpt a whole paragraph out of nothing but static? Well, a new type of AI promises to do just that. And it might just change everything we thought we knew about AI language.
Right. So we've all had fun with AI that can write poems, emails, even lines of code. But have you ever really stopped to think about how it's stringing those words together? It's not magic, you know. It's a very specific design choice. And as we're about to see, that choice, it comes with some pretty serious limitations. For years now, the AI world has pretty much been dominated by a single approach. You've heard the term autoregressive large language models, or LLMs. That's the engine behind most of the AI tools that we use every single day. And here's where the two paths really split. The familiar autoregressive models, they're like a meticulous writer, carefully picking one word, then the next, then the one after that, all in a straight line. But these new diffusion language models, or DLMs, they're completely different. They're not writers. They're more like sculptors. They start with a chaotic mess, literally just random noise, and then they refine the entire block of text at the same time until a finished, coherent idea emerges. Now, that old one-track mind approach, it creates some real problems. If the model makes one tiny mistake early on, that error can just snowball and ruin everything that follows. Plus, going one by one is just slow. It's a huge speed bottleneck. And trying to control the output, like telling it to write exactly 50 words, it's a constant battle. Surely there's gotta be a better way.
Well, there is. And the solution, believe it or not, is coming from a totally different part of the AI world, image generation. Yeah, the very same technology that creates those mind-blowing, photorealistic images from a simple text prompt is now being taught how to work with language. The perfect analogy is to think of it like restoring a blurry photo. You start with something that's totally indecipherable, right? Just a screen full of static. And you gradually, step by step, bring it into sharp focus. Diffusion models do the exact same thing. But instead of working with pixels, their raw material is language itself. The technical name for this whole process is denoising. The model is trained to do one thing and one thing only: reverse chaos. We literally show it a perfect sentence, then we intentionally corrupt it, turn it into noise, and then we teach the AI how to bring it back. So it learns to take that random static and sculpt it, bit by bit, back into meaningful text. So how does this actually work under the hood? I mean, how do you take an idea that was born from pixels and apply it to something as structured as words? Let's get into the mechanics. Let's be really clear on the definition here. A DLM is non-autoregressive. This is the key. It doesn't think step by step. It thinks holistically. From the very beginning of the process, it's working on the entire sentence, the entire paragraph, all at once. It sees the whole picture from start to finish. Okay, but this brings us to the elephant in the room. It's easy to picture adding noise to an image, just make it grainy or blurry. But how do you add noise to a word? This was the fundamental challenge that researchers had to overcome. And here's the heart of the problem. Pixels in an image, that's what's known as continuous data. You can nudge a color value just a tiny, tiny bit. But words, they're discrete. They are specific individual items from a fixed dictionary. You can't have half a word. You can't add 10% noise to the word cat. The word is either cat or it's something else entirely. There's no in-between. So the researchers came up with two really clever workarounds. The first approach was to say, okay, let's make it continuous. Instead of messing with the words themselves, the AI works with their embeddings. These are rich mathematical representations of a word's meaning, and since they're just numbers, you can add noise to them. The second approach just embraces the problem head-on. If you can't make a word a little bit noisy, then just corrupt it completely by replacing it with a special mask token. This visual shows you that denoising process perfectly. The model starts with a totally random cloud of points. It's pure chaos, and it's trained to reverse that process. Step by step, it refines that noise until a clear, structured pattern emerges. The key insight here is that this principle works for anything, not just images. Whether the model is revealing a chessboard or sculpting a coherent sentence from a mess of noisy embeddings, the fundamental process is exactly the same, creating structure from pure noise. Okay, so we've waded through all that technical detail. So what? Why does it matter? Well, it matters because this new architecture brings some absolutely game-changing advantages to the table. So, just how fast are we talking? Well, ByteDance has a model called Seed Diffusion, and it clocks in at a staggering 2,146 tokens per second. By generating everything in parallel instead of one by one, it completely shatters the old speed limits. And let me be clear, this isn't some niche academic project tucked away in a university lab. We're talking about major players like ByteDance and Google who are investing heavily in this. Models like Seed and Gemini are pushing this technology into the mainstream right now. Now, your first thought is probably, okay, if it's that much faster, the quality must take a hit, right? That's the usual trade-off. But here's what's so exciting. There is no trade-off. The benchmarks are showing that these new diffusion models aren't just setting speed records, they're also achieving quality scores that are highly competitive with even the very best traditional models out there. So let's just put it all together. You get a massive speed up from parallel generation. You get this inherent self-correction because the model can fix its own mistakes as it refines the whole thing. And, maybe best of all, you get incredible fine-grained control. You can easily tell it to fill in missing text or to enforce a perfect structure for something like code. The performance is impressive, no doubt. But the implications, well, they go a lot deeper. This shift in how AI is built is raising some fascinating questions about the very nature of AI thought. And this has kicked off a really cool debate online. As one Reddit user pointed out, we humans might speak our words one at a time, but we don't think that way. Our brains seem to grab and analyze the whole idea at once, subconsciously, and that process feels a lot more like this holistic diffusion method than it does a simple left-to-right assembly line.
And this really gets to the core of the whole thing. Is the one word at a time method we see in most AI just a limitation of our mouths and our keyboards? Or does the holistic, all-at-once refinement of a diffusion model actually get us closer to how our own minds really work, processing everything in parallel before a single word ever comes out?
And that leaves us with one final, pretty provocative question. For years, we've been building AI that's gotten incredibly good at mimicking the output of human intelligence, our writing. But with diffusion models, are we taking the first real steps toward an AI that mimics the process of human thought itself? What happens next is truly anyone's guess.